There we go. All right, happy Tuesday. Can you believe we're in week 9? This is the last week of new material. So chapter 10, the last week of the new stuff. Some of my favorite stuff is here. I think I say that every week though. So I need to just quit saying that some of my favorite stuff, but it's all good. It's funny that when I first started teaching stats the first term, I really didn't enjoy it. And I was like, why am I teaching this? It's not very mathy, but I've really grown to love the topic. So I love teaching hypothesis testing, which is what we're going to learn this week. And pretty much, I think everything except for the first class, because the first class is just all vocabulary and not much fun. I think everything but the first class is my favorite. It's all good. So today we're not going to do much math. Today I'm introducing a new topic. We're going to learn about hypothesis testing, and we're going to learn some information about that. And then all of our math is going to be relegated to Thursday. So Thursday's super math heavy. So we're going to talk about what the null and alternative hypotheses are, what those look like, how to write them. We're going to look at type 1 and type 2 errors, and then talk about how we write the conclusions to our hypothesis tests. Then we're going to just dip our toe into 10.2. We're not going to actually get to the math, but we're going to talk about what basically the two different methods for hypothesis testing and what we're looking for. So that is what we are doing today. So you'll have all the information you need to do the 10.1 assignment after today, but you won't have enough to do 10.2. So we'll finish up 10.2 and 10.3 on Thursday. So that's today. That's what we got going on today. All right. So a hypothesis is just a statement regarding a characteristic. So we say what we think based on, usually it's based on some observation or just what we think based on circumstances in the world. We would make a statement that something we believe might be true. So that would be our hypothesis. It's like you believe that the average whatever is greater than something else. Like I believe that the average commute to work is greater than 15 minutes. So that's a hypothesis. Then after I make that hypothesis, then I'm going to do all of the work that I need to try to support that hypothesis. So that's what we're going to do. Now, there are more complicated hypothesis testing that has more than one population parameter, but we're going to be looking at just one at a time. So that's what we're doing with our 10.2 and our 10.3. So, but you can do more complicated ones where you're looking at more than one parameter. We're going to do proportions and we're going to do means, and that's it. Except for in our big opening examples, one of them is going to have standard deviation, but that's okay. So here's some examples of claims that we would make with a hypothesis. So in 2008, 62% of Americans regularly volunteered their time for charity work. A researcher believes that percentage is different today. So this is a claim that we might see. So a previous study at some point said that 62% of adults regularly volunteer for the charity work. And then based on maybe this researcher has just talked to a lot of people that volunteer for charity work and is like, I just think it's different. So different could be greater than, or it could be less than. If he just doesn't think it's 62% anymore. So this is our first hypothesis. So here's another one. According to a study published in March 2006, the mean length of a phone call on a cell phone was 3.25 minutes. A researcher believes that the mean length of a call has increased since then. So this is a greater than. So he thinks that the average length of a phone call is longer than 3.25 minutes now. So based on whatever kind of observations he's made, based on people he's talked to, whatever, he hasn't actually collected the data yet. He just believes that people are talking longer on the phone now. Here's the third one. Using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces. With new equipment, the quality control manager believes the standard deviation has decreased. So in this case, they actually have new equipment. So he thinks that with this new equipment, the amount of wine in the bottle is more consistent. So this new equipment like fixed whatever errors they were having, and he thinks that they're getting a more consistent amount of wine in the bottle. So he thinks that that standard deviation has decreased. So these are the three ways that we're going to see our hypotheses. We'll see different, which means greater than or less than. It could be greater than, it could be less than. You'll see something that actually says that something's longer or something has increased. That's going to be our greater than. And we'll see that something is decreased, and that'll be our less than. We're going to keep touching on these three as we go through our explanations tonight. All right. So when we use sample data here, because if we use the entire had access to the entire population, we wouldn't really need to be doing hypothesis testing. So this is all going to be sample. It's going to be sample data. And yeah, that's it. So we're going to be using little s for standard deviation. We'll be using our X bar for mean. So this is all sample data. So what we do with hypothesis testing is we're going to make a statement, and then we're going to test this statement regarding the characteristic of our population. We're only going to do one population hypothesis testing. Now, if you decided to do a two population testing, that would be extra credit on your end of the year, your final project. You would need to learn that on your own. That I believe is in chapter 11 in our textbook, which if you if you don't actually have the textbook and you want uh, later chapters to dig into, let me know and I can send you a PDF. Just send me an email and ask for it, and I can send you a PDF if you want to dig into later chapters. I'm happy to do that. It's not a problem at all. But we're only going to be testing one population. Okay, steps in hypothesis testing. The first thing we're going to do is you're going to make a statement regarding the nature of the population. So, like, for example, I might say that, as I said before, I think that the average commute to work is greater than 15 minutes. So that would be the statement. Now, I don't have data yet. I have not collected any data on that. I'm just making a statement based on what I think. The second step is you actually collect your data. You take a sample. Uh, and so I'm going to take my sample and then use that sample to test my statement. Once you take your sample, then we have math that you're going to do in order to determine whether the statement that you made is plausible, whether it's likely. If your statement is likely, then we'll take our next steps and we can draw a conclusion. We can apply it to the population. So these are the steps that we're going to be going through. Now, you will be given the statement. You will be given number one. They will collect the data for you. So one and two is going to be done for you. You're just going to have to, I'll show you how we're going to write it out and make it look pretty and how we're going to do the math on that. But one and two will be done for you. Unless you're using it for your final project, then obviously one and two are things you've done. Any questions before I move on? All right. So the null hypothesis. The null hypothesis is what we're testing. So null hypothesis is like the old study that we did, the old study that we're looking at. And this is the statement that we're assuming is true until we have shown otherwise. This right here is how we write it. H sub 0, also called H naught. I will write this down. So we will call this H naught. That sub 0 is not. So this is like an initial statement. Whenever something is sub 0, has the subtext of the 0 there, it's always like the initial statement. So this is always going to have an equal sign. Always has an equal sign. and we always assume it is true until evidence shows otherwise. This is your null hypothesis. Give you a second to write your little notes on there. Okay. The alternative hypothesis. This is sub 1. That also sometimes is written as this. It could be written either sub A or sub 1. Either one is fine. I've seen it both ways. I'm not sure which one my open math uses, but they're exactly the same thing. If you see H sub A or H sub 1, it's the same thing. So the alternative hypothesis, this is the thing we're trying to find the evidence to support. So this is I think that the average commute is greater than 15 minutes. So the greater than 15 minutes, that would be my null or alternative hypothesis. That's what I'm trying to find evidence to support. I'm trying to prove it might be true or show that it's plausible. That's the alternative hypothesis. So both of those things are going to be required in every problem, having a null and an alternative hypothesis. And this will never be equal. It'll be either not equal to, or it'll be greater than, or it'll be less than, never equal. It's never going to be equal. It'll be not equal to, it'll be greater than, or it'll be less than. It's never just going to be equal. The equal is only for the null hypothesis. All right, moving on. All right, so here is what our tests look like, our hypothesis tests. If you see the word different, it is a two-tailed test. Our null hypothesis will say like some parameter equals a certain value, and our alternative hypothesis will say not equal to. This is called a two-tailed test. If I was to draw my normal curve, I would be looking for, we create a confidence interval basically, and I'm saying, does the probability of my alternative hypothesis land out here or out here? So it can be greater than, or it can be less than. I'm going to go into more detail of what these look like in a minute. But the two-tailed test is always says the word different, and it's going to be not equal to. A left-tailed test. So a left-tailed test is going to say something like less than, or it might say has decreased, or it might say smaller. Something like that. It's going to have words that indicate less than, or that it's smaller than, or it's gone down, or whatever. So if I was to draw my normal curve, a left-tailed test, I'm looking for, does my alternative hypothesis land out here? That probability, does it land down there in the less than area? The right-tailed test, you're going to see words that mean greater than. Greater than, has increased, larger. So any words that might mean greater than, that's what's going to be the right-tailed test. So drawing my curve, that is the ugliest curve. Let's try this one again. And it's not getting any better. So I would be looking for, does my alternative hypothesis land me up above and the right side of my curve? So these are the three types of null and alternative hypotheses we're going to set up. Don't worry, we're going to do several of these, and hopefully it'll make sense to you. I'm going to give you a minute to write stuff down. All right. Anyone need a moment? Are we good? Okay. So the null hypothesis, the status quo, no difference. It always has equal. The null hypothesis is true until we show something different. We are looking for evidence to support the alternative hypothesis. That's what we're trying to basically prove. We're trying to show that the alternative hypothesis is likely true. Obviously, we're statisticians. We don't deal in absolutes, so we won't say it's absolutely true, but it's likely true. So this is basically what we're saying. All right. So we're going to write in our null and alternative hypothesis, and we're going to determine whether it's two-tailed, left-tailed, or right-tailed. Right. So in 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that this percent is different today. So my null hypothesis is always equal. So before we even talk about what tail it is, I'm going to write my null hypothesis, H naught, and we're looking at percent. We're looking at a probability. So I'm going to put a P equals 0.62. Always equals. And we're looking at the proportion of Americans volunteer for charity work is equal to 0.62. This is my null hypothesis. My alternative hypothesis, so this says the word different, therefore it is a two-tailed test. When we have a two-tailed test, we always use not equal to. These numbers will always be the same. The only thing that changes is we change from H naught to either H1 or HA, and we change the sign from equal to not equal. No matter what kind of test we have, the numbers are going to be the same. So this is my null alternative hypothesis, and it's a two-tailed test. Any questions on this? Right. It is printed on the next slide. I'm gonna bop on to the next one. All right. According to a study published in March 2006, the mean length of a phone call on a cell phone was 3.25 minutes. A researcher believes the mean length of a call has increased since then. Has increased. This is a right-tailed. Because it says has increased, it is greater than, so we're looking at the right side of our curve. So my null hypothesis, once again, always an equal sign, but we're looking at mean, 3.25 minutes. My alternative hypothesis, my mean is greater than 3.25 minutes. I don't care whether or not you actually put the units. It's not super important. And I think that my open math I don't think it has units on it when you're doing them. So the minute, that's not super important to me. As long as your conclusion says minutes, I think I'm okay with it. Questions so far? Are we doing okay? Okay. Let's do the last one. Oh, all the stuff I just said. All right. So using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces. With new equipment, the quality control manager believes the standard deviation has decreased. They believe that it has decreased. It's a left-tailed test because it is decreased. Because they think it is less than that now. So this is a left-tailed test. So my null hypothesis, standard deviation equals 0.23 ounces. My alternative hypothesis, standard deviation is less than 0.23 ounces. because we believe it has decreased, it is less than. Now that you've seen all three of them, any questions? All right. I already did that one. Okay. So this will give us our type 1 and our type 2 error. Type 1 and type 2 error can be kind of confusing. So when you're taking your test, you're going to want to keep this handy. And I believe that there's a question about this on the next quiz. There's a question about type 1 or type 2 error. So first, let's talk about the good, the true, the correct decisions. If you you reject the null hypothesis when the alternative hypothesis is true, you've done the right thing. This is the correct decision. So if the alternative hypothesis is true, you need to reject the null hypothesis. This is great. This is what we do. So number two, if you don't reject the null hypothesis, and because the null hypothesis is true, or you don't reject the null hypothesis because the alternative hypothesis is not true, this is good. So if it turns out that the null hypothesis is true, you're not going to reject it. So number three, so this is a bad one. Reject the null hypothesis, but the null hypothesis is true. This is not good. This is type 1 error. So if you reject the null hypothesis, but you were not able to show evidence to support your alternative hypothesis, then this is a type 1 error. So if you don't reject the null hypothesis, but you have proven that the alternative hypothesis is true, then this is a type 2 error. So when you don't reject, but you should have, it's a type 2 error. But if you reject when you shouldn't have, it's a type 1 error. I'm going to write these words down. I don't know if they're going to help you. Reject when you shouldn't have. And this is don't reject when you should have. So these are type 1 and type 2 errors. So in the grand scheme of things, type 1 and type 2 errors, it's not super important. I will tell you that there's a question on the test regarding the type 1 and type 2 errors. It's asking you, I believe it asks you to state what that would be. So there is a question there. I do grade fairly lenient on it. So don't leave it blank. I grade fairly lenient on these because they can be confusing. Just do the best you can. But just keep this page handy. Keep this page. It'll help you to write whatever you need to write for that test question. And I believe that in the quiz, it asks you which one it is. So pay attention to that. Questions on the type 1 and type 2 error. We're going to do some examples. Thing I don't like about the examples, though, is that they're very wordy and they get kind of confusing. So let's take a look. So we're going to talk about what a type 1 error would mean and what a type 2 error would mean in these examples. So in 2008, 62% of Americans regularly volunteered for charity work. A researcher believes this is different today. So a type 1 error. So if the researcher rejects the null hypothesis when the null hypothesis is true, so if they say that the proportion doesn't equal 0.62, but the proportion actually did equal 0.62, that is a type 1 error. A type 2 error, so if the data shows that the number of people who volunteer for charity work is in fact not 62%, yet we don't reject the null hypothesis, then that would be a type 2 error. And I know it's a little bit confusing. These ones are tough. Thankfully, very, very small portion of your, and if you got all of these wrong, it if you got all of them wrong, it would totally be okay. It would totally be okay if you got all of them wrong. You could still get a very strong A on the test, getting all the type 1 and type 2 error ones wrong. So it's not going to affect you terribly. All right, let's do another one. According to a study published in March 2006, the mean length of a phone call was 3.25 minutes. A researcher believes that the length of the call has increased since then. So let's take a look. A type 1 error. If the evidence leads the researcher to conclude that the average is greater than 3.25, but the actual length of the call is 3.25 minutes, that would be a type 1 error. Type 2 error, if the researcher doesn't reject the null hypothesis, but the actual mean length of a phone call is greater than 3.25 minutes, that's a type 2 error. Okay. So this is something important here. So it's not necessarily important. I will never, the only time I'm really going to ask for it, there is a quiz question. There is a quiz question. So on the quiz question, if your answer on the quiz question is type 1 error, it's going to ask you what the probability of a type 1 error is, or of that error is. That probability is alpha. If it asks you, or if you determine that it's a type 2 error in your homework or in your quiz, the probability of that happening is beta. So make sure that you put that there. That's what your answer would be to that probability. If it's a type 1 error, say the probability is alpha. If it's a type 2 error, say the probability is beta. That's it. You don't have to get really deep on that probability stuff. If it's type 1, it's alpha. If it's type 2, it's beta. That's it on the probability part. Right. Questions? Okay. So I just said this. So the probability of making the type 1 error is alpha. So alpha is the level of significance in a hypothesis test. And it is the probability of making a type 1 error, but it's not super important to remember that for the purposes of hypothesis testing. So this alpha is essentially the same thing when we were using our confidence intervals. Remember the alpha from our confidence intervals? It's the same thing. It is the area in the tail. The difference is, so hypothesis testing, we're going to create confidence intervals. So for a two-tailed test, we create a confidence interval exactly how we created the confidence interval in chapter 9. It's going to be exactly the same for a two-tailed test. We'll do, this would be alpha divided by 2. This would be alpha divided by 2. We're going to use those z-scores or t-scores, exactly the same. But when we are a right-tailed test or a left-tailed test, oops, I didn't mean to erase that whole thing. Let's go back. If it's a right-tailed test or a left-tailed test, our confidence interval looks a little bit different. A left-tailed test, this would just be alpha. The area in that tail there would just be alpha. And it's going to be a negative value. If it is a right-tailed test, it's basically we're just doing, well, one part of the confidence interval. But this, so right-tailed test, it's going to look like this, and the area in that side of the tail is alpha. So it's just a little bit different than the confidence intervals in the sense that our right-tailed and our left-tailed look different. But if it's a two-tailed test, it is the exact same confidence interval we just created in our last unit. So it makes it kind of easy there for the two-tailed tests. I'm going to go a little bit more in depth here, but any questions so far? All right. Now, this isn't, I'm not even going to ask you this question, but As the probability of a type 1 error gets larger, the probability of a type 2 error gets smaller, and vice versa. I don't think this is asked anywhere in your homework. It's not asked on the test, but it is the case. If you move on to stats 244, I don't know how many of you are going on to 244, but they go a little bit deeper into this stuff. And so they'll kind of refer back and they'll bring all of this back in. And they pretty much act as if you've never seen it before, and then they build on it. So even if you don't quite understand the type 1 and type 2 error here, you'll get it again if you take 244. If you don't, it will never affect your livelihood. So try not to freak out if this is confusing. Okay, so this is super important, super, super important. We never accept the null hypothesis. I'm even going to highlight this. This is super important. We don't accept the null hypothesis. We don't have access to the entire population. We don't know if we just happen to get a really good sample or a sample that supports our null hypothesis. We don't know because we can't do get the whole population. We say that we either say that we do not reject the null hypothesis, or we say we reject it. It's kind of like you don't ever declare a defendant innocent. You just say they're not guilty. So you will either say that you reject, or you will say that you fail to reject. You can say fail to reject, or you can say do not reject. I usually say fail to reject because I like that better. But please make sure that if you are writing out a conclusion, say one of those things. Make it very clear that you either rejected or you did not reject. Make it very clear in your answer of which one you did. Don't just say there's not sufficient evidence to support. Say, I reject the null hypothesis, or I do not reject the null hypothesis. Make sure you clearly say one or the other. Okay. So let's go down a little bit more. All right. So according to a study published in March 2006, the mean length of a phone call on a cell phone is 3.25 minutes. A researcher believes the mean length of a call has increased since then. Suppose the sample and evidence indicates that the null hypothesis should be rejected. So they word things differently than I do. I'm not the biggest fan of the way that the textbook words it. I'm going to show you and then I'll write my own beneath it. No matter what, it's a lot of words. So here's what the textbook says. Whoops. The statement in the alternative hypothesis is that a mean call length is greater than 3.25 minutes. Since the null hypothesis is rejected, there is sufficient evidence to conclude that the mean length of a phone call is greater than 3.25 minutes. So here's what mine would state. There is sufficient evidence to conclude that the mean length of a phone call, is greater than 3.25 minutes. Therefore, we reject the null hypothesis. I mean, we're saying a lot of the same things, but I just feel like they throw some extra things in there. Like, I didn't feel like this whole thing right here is necessary. I don't feel that that's necessary. You could write all of this other stuff if you wanted to write it exactly, you see here, exactly like this right here without even that first thing. You're fine. Make sure, though, that you make a statement in there that the null hypothesis has been rejected. Just make sure that that word is in there. Questions on this conclusion? Okay, we're going to do another one. Suppose the sample evidence indicates that the null hypothesis should not be rejected. State the wording of the conclusion. So now we're going to not reject. Since the null hypothesis is not rejected, there's insufficient evidence to conclude that the mean length of the phone call is greater than 3.25 minutes. In other words, the sample evidence is consistent with the mean call length equaling 3.25 minutes. You could write just this right there. What I would probably write, this is my own wording. There is insufficient. You can say not enough evidence if you want. I like the word insufficient. If you say not enough evidence, that's fine. Insufficient evidence to support the mean length of a cell phone call greater than 3.25 minutes. So we fail to reject, fail to reject the null hypothesis. So I haven't taught you how we're going to support it, what that evidence is going to look like. I haven't taught you that yet. But on your test, when you're writing a conclusion on your test, I'm going to expect you to tell me how you know in your conclusion, because I'm going to see all of your math and you're going to write fail to reject or you're going to write reject, but I want you to tell me how you know. Once we actually get to the math, I'm going to make it really clear what I want that to look like. But I want you to tell me that, your test statistic was greater than your critical value or whatever your reasoning is. I want you to show me. I want you to explain it to me. Tell me why. Because that's going to show me you clearly understand what you're doing, and that'll get you your full points. Uh, on your test, you're going to be giving me every single step of the hypothesis test. I'm going to show you exactly what I want that to look like in your work. I don't want there to be any ambiguity there. I'm going to be very, very clear. This is exactly what I expect you to show me. And so, because I want to make sure that you know exactly what that's supposed to look like. Obviously, we don't have the math yet, but that's going to come on Thursday. Any questions on these conclusions? Okay, let's move on. All right, so we are now in 10.2. You have enough information to do the 10.1 homework right now. If you keep track of that sort of thing, 10.2 is here. Now I'm going to show you, I'm not going to show you the math to get to the evidence, but I'm going to show you what evidence we're looking for. Okay. A researcher obtains a random sample of 1,000 people and finds that 534 are in favor of banning cell phone use while driving. So our p hat was about 53.4%. Does this suggest that more than 50% of people favor the policy? Or is it possible, did we just happen to get a survey where the majority of people favor the policy? So are we saying, do we have evidence to show that that actual number is greater than 50%? Or did we just happen to get a good sample? Would it be unusual for us to obtain a sample of 0.534, a p hat of 0.534 or higher, if the actual proportion is 5%? So that's what we're looking at here. That's what we want to know. We want to know, is that probability so small that it would be unusual to find that? That's what we're looking for. So if something is statistically significant, then if it's extremely unlikely that something happens, it is considered statistically significant. So if I took a sample of something and let's say I took a sample and the probability of getting that average of that sample of whatever it is less than 5%. Let's say it was 2% probability. That would be statistically significant because that would be unlikely. Because in general, we look at 5%, right? Anything that occurs less than 5% of the time is considered unusual. So if I take a sample and the probability of getting a sample like that is less than that 5%, then I'm going to have to rethink everything because that is a statistically significant sample. Hopefully that made sense. I'm not going to ask you to use the word statistically significant, but that's basically what it means. All right. So to determine if a sample is statistically significant, first thing we look at, NP times 1 minus P has to be greater than or equal to 10. This just does not go away, does it? Just does not go away. I bet you guys wish it would go away, but it's not going away. And then also, we need to make sure that our sample size is less than 5% of our population. Got that. We're good. This is how we determine our standard deviation. This is when we're dealing with proportions, because in 10.2, we're going to be dealing with proportions. So we'll use our new standard deviation or this standard error. So we're going to use this. So when we created our hypothesis or our confidence interval, so this one is a greater than or equal to, so that would be a right-tailed test. So when we created our confidence interval, I have a certain z-score. I have a certain z-score that corresponds with this right here. So this tells me that I am supporting my null hypothesis as long as my sample, the probability of my sample lands in here somewhere. If my sample proportion lands, the probability of it happening lands in there somewhere, I'm good. I am, I'm supporting my null hypothesis. However, if the probability of my sample being whatever it is out here, if it lands out here past that z-score, or if it is more standard deviations away from the mean, then this line right here, so if I'm more standard deviations away from the mean than that line, then it is statistically significant and it would cause me to reject the null hypothesis. So my sample lands me out here, more standard deviations away from the mean than that line, then it is statistically significant and I'm going to reject the null hypothesis. That's what's going on here. And I know once we're actually doing examples, it's going to make more sense, but I just want to kind of give you an idea of what's happening. We create that confidence interval, and if my sample lands me outside of that confidence interval, then I'm going to reject that null hypothesis. That supports my alternative hypothesis. All right. Hey, look, it gives me a nice pretty. This is the sampling distribution of my of the thing that I just did with the whatever that my example is, the banning cell phone use while driving. So this is my sampling distribution. This is one standard deviation away. Generally, we are going to go more than 2 standard deviations away. This is just a nice pretty picture. So as I said, we're going to consider this. This is the classical approach. You're not going to have to remember which approach is which. You can kind of, most of the time, at least for your test, you're going to get to choose which approach you like. The My Open Math is going to tell you which approach it wants you to use. So this one right here. So where if our sample proportion is too many standard deviations away from our p hat, then it's going to be statistically significant. So 2 is kind of our rule of thumb, but our alpha is going to determine how many standard deviations we can be away. But right now, we're just going to say 2. So let's take a look. So 5.34, this 0.534 has a z-score of 2.15. 2.15 is more than 2 standard deviations above that 50%. So we would reject the null hypothesis because it is an outlier. Because it is more than 2 standard deviations away, we will reject the null hypothesis here. Because I compared them and it's more than 2 standard deviations away. Therefore, we're going to reject the null hypothesis. We have questions so far? I know this is a lot.
So
All right.
just to clarify, sorry,
Oh,
just to clarify, we're taking the z-score of the p hat.
yeah, yes, well, no, you take, okay, yes, 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 that's exactly what you're doing. So you find the standard deviation of your p, not your p hat. So of your mean, you find the standard deviation of your mean with your sample size. That's the standard deviation we're looking at. The p hat is what we're finding the z-score of.
Okay.
Does that make sense?
Yes, thank you.
Okay, good. Yes. Beautiful. You're getting it. It's going to make, once we're actually mathing with it, it's going to be even better. This really, it doesn't get super complicated. It looks more complicated than it is. So our other way of doing this, so I found out what is the probability of getting this z-score right here. And it is 0.0228 was the probability of getting that z-score. That is definitely less than 5%. Because remember that 95% of all of my data is within 2 standard deviations of the mean. That is a super small value right there. That's even less than 2.5%, which usually when we have tails on both ends, that's what we look at. This is a super small probability. Because this probability is so small, it is clearly would be unusual if the actual proportion of people who believe that you should ban cell phones while driving was 50%, it would be really unusual to get a sample of 53.4%. It would be unusual. Therefore, we would conclude that the actual percent of people who believe that cell phones should be banned by driving is greater than 50%. That's what we're looking at. So we're rejecting that null hypothesis that 50% is no longer true. All right, so this is lots of just same thing I just said. It's just mathing it out. All right, so our other approach, so we already looked at this one when it's too many standard deviations away from the mean. That is the classical approach. The p-value approach. So instead of using z-scores with the p-value approach, we're just looking for that probability. So you can either compare the z-scores. So this z-score right here, that's a really ugly. So this z-score right here, z-score is 2. Then I would look at the z-score of my sample. So I'm going to put, this is not standard notation, but I just want you to be able to like distinguish them. My z-score of my p hat was 2 point, I don't remember if it was 1.5 or 1.8, but I'm going to just call it 2.15. So I'm comparing, this is classical approach. I'm comparing my z-scores. The z-score for my p hat is farther than the z-score of 2 that we agreed upon was the edge of my confidence interval. Since it is farther away, this is why we reject the null hypothesis. Okay, so the other approach is the p-value approach. So with the p-value approach, I think I have that on the other screen, do I? Yes. So with the p-value approach, we are given an alpha. The alpha is our significance level. The alpha is it's a probability of making a type 1 error, but I don't really care about that. But it is like an acceptable probability or acceptable probability for my sample. That would be what my alpha is. It would be acceptable if I had anything, any probability greater than 5%, let's say. So if my p-value is smaller than that, then I'm going to reject the null hypothesis. So let me see if this shows it better. So this right here, I don't like that one either. So eh, I'm looking for that one that has an alpha. So if my alpha is 5% and I get a probability of 1.58%, since this number is smaller than the 5% we agreed on, I would reject the null hypothesis. That's what we do with p-values. P-value is just a probability. It's the probability of getting a sample like that. So those are the two ways that we do it. We compare z-scores or we compare the probability with the alpha we're given because the alpha is our like acceptable probability. Let me see if the next screen says it better. Okay, this is it right here. If the probability of getting a sample proportion as extreme or more extreme than the one obtained is small, then we reject the null hypothesis. So I've started saying this to my high school kids because it gets them to remember things and it makes them giggle, but this is perfect. It's if the P is low, reject the hoe. The P is low, reject the hoe. This is what I get my high school students to remember it. And so far, this is the third term I've used it in college, and it works. You're going to remember it now. If the P is low, reject the hoe. If you have a low P value, you're going to reject the null hypothesis. I think that was it. So there's a whole lot of information I gave you guys today. And if you just want to do the 10.1 homework and kind of put 10.2 so far into in your pocket and just save it till Thursday, I would recommend that because Thursday we're going to do all the math and this is all going to make a lot more sense. But at least you kind of have an idea of where we're going, confidence intervals and just comparing things. You kind of have an idea and it's all going to make sense and come together beautifully on Thursday. So before I close out for the day, you have any questions for me while we're still recording?
I've got a question.
Yes.
So I watched all your videos and I did do the homework.
Uh-huh.
Um, my frustration was with the rounding in my open math.
Uh-huh.
And I just kept doggedly getting question after question until I got one where the rounding worked.
Okay.
Can you give us any tips or tricks? Like, is rounding to the thousandth place? Or,
Okay,
I mean, sometimes I would request 5 questions in a row until I got one that would actually work.
so pay attention to what it's telling you because a couple of the Z scores, they when they give them to you, they round them to three decimal places. I don't know if you've noticed that. So it's like 2.545, and there's like a few of them that give you three decimal places. Much of the time, my open math wants you to round your Z scores to two decimal places. And sometimes that's what will do it for you. Sometimes that's what you need to do. I generally, when I'm doing my math, I won't do any rounding at all until the very, very end. I,
Generally, what I do too. I'll leave everything in the calculator and then just round to
yeah,
the
that's
end.
usually
Sometimes
what I
that would
do.
not work.
And if you get there's a couple of different assignments where my open maths rounding kind of sucks. But if you keep getting them wrong and you know you're doing it correct, send me a message. I will take a look at it and if I can see that you're just having issues, I will do the problem myself. And if I notice that my rounding matches your rounding, I'll just give you credit for it. So yeah, because sometimes my open math, I don't know if they're how they're rounding mid calculation. I don't know what they're doing. I don't know if they're doing three or four decimal places. Are they doing two?
Yeah.
Usually, Usually, if you just change your z-score to rounding to two places, usually they're fine, that it'll
Okay.
match.
Okay,
So
because
try that.
10.2 was the worst one we've had this year as far as getting it to
Really?
accept answers.
Oh, I'm so sorry. Yeah,
Yeah, I
please
got through it,
change.
but yeah.
I have to always remind myself because it is frustrating. I agree. I have to keep reminding myself, this is free software. This is free software. When I was at RCC, the software we used was over $100 a term.
Mhm.
And so I'm like, okay, this is free software. I'm just gonna just grin and bear
Head
it.
down and be happy for the free.
I
My other
know.
question is that in one of your videos, it said something about quiz 7 being extra credit. Was that just for that year?
It was just for that year.
Uh,
I've
Bummer.
I'm sorry. Yeah, I have found that
Okay.
yeah, yeah, I feel like no, it's not. I'm not even gonna go there.
Couldn't hurt to ask. Okay,
That
thank
was
you.
that was COVID year and things
Yep.
were different.
Gotcha.
So no, you got to do quiz 7. Quiz seven's not that hard though. You'll be fine. All right, any other questions while we're recording? All right, I'm going to turn the recording off.